Hi, I'm Mr. Parker and this is question 7 on the OCR Mechanics 2 paper from January 2009. For more questions on this exam paper, click the link here or check in the video description. Two small spheres P and Q are free to move on the inside of a smooth, hollow cylinder in such a way that they remain in contact with both the curved surface and the base of the cylinder. The mass of P is 0.2 kg, the mass of Q is 0.3 kg, and the radius of the cylinder is 0.4 meters. P and Q are stationary at opposite ends of the diameter of the base of the cylinder. The coefficient of restitution between P and Q is 0.5. P is given an impulse of magnitude 0.8 Newton seconds in a tangential direction. In part 1, we need to calculate the speeds of the particles after P's first impact with Q. Later in the question, we're going to have to consider the impact between P and Q, but first we need to know what speed P is travelling at when it first collides with Q. To do that, we'll use the fact that in the question we're given that the impulse is 0.8 Newton seconds, and impulse is defined as the change in momentum. Change in momentum is equal to mass times the change in velocity, and initially as it's at rest it has no momentum, so that means 0.8 equals the mass 0.2 multiplied by the velocity v. To find v, we divide through by 0.2. 0.2 goes into 0.8 4 times, so the velocity is 4 meters per second. So in our diagram before the collision, we've got P with a velocity of 4 meters per second and Q at rest, with P having a mass of 0.2 kilograms and Q having a mass of 0.3 kilograms. After the collision, we'll say that P has a velocity Vp and Q has a velocity Vq. I'm going to assume that after the collision they're both travelling in the same direction, but if that turns out to be wrong, all that will happen is that the quantity Vp will end up being negative. The masses are obviously the same after the collision as before the collision, and I'm going to start off by considering the law of restitution. That says that the coefficient of restitution is equal to the separation speed divided by the approach speed. We're given the coefficient of restitution in the question, that's 0.5. For the approach speed, one particle is travelling at 4 meters per second, the other's at rest, so we can just put that in as 4. And as Q is the particle in front, that must have a higher velocity than P, so we'll write down the separation speed as Vq minus Vp. Multiplying up by the 4 on the bottom of this fraction gives us 2 equals Vq minus Vp. And if we add Vp to both sides, we get Vq equals 2 plus Vp. Next up, we'll think about conservation of momentum. Before the collision, only P has momentum, and that's going to be equal to 0.2 times 4. After the collision, the momentum of P will be 0.2 multiplied by Vp plus 0.3 times Vq. 0.2 times 4 is 0.8, and using the equation earlier where Vq equals 2 plus Vp, we can substitute that into our conservation of momentum equation for Vq, giving us 0.2 Vp plus 0.3 multiplied by 2 plus Vp. If we expand out the bracket on the right hand side, we'll get 0.3 times 2, which is 0.6, and we'll get 0.2 Vp plus another 0.3 lots of Vp gives us 0.5 Vp. Subtracting 0.6 from both sides and then multiplying both sides by 2 gives us Vp equals 0.4 meters per second. Now that we know Vp, it's easy enough to find Vq, we just need to add 2 to it, meaning Vq equals 2.4 meters per second. In part 2, we're told that Q subsequently catches up with P and there is a second impact. We need to calculate the speeds of the particles after this second impact. So we have a new before and after diagram. This time notice that I've put Q on the left hand side because it will have travelled all the way around the cylinder and it will be coming up behind P. In the last part of the question we worked out the velocity of Q was 2.4 meters per second and the velocity of P was 0.4 meters per second. The particles still have the same masses as previously, and we are trying to find the speeds of Q and P after the collision. Once again, we'll start by considering the law of restitution. The coefficient of restitution is the same as we got the same two particles, that's 0.5, but this time the speed of approach will be 2.4 minus 0.4, which gives us 2. This time Vp must be travelling faster after the collision, so our speed of separation is Vp minus Vq. Multiplying up by 2 and adding Vq to both sides gives us Vq plus 1 equals Vp. Now that we've got an equation linking Vq and Vp, we can think about conservation of momentum. Before the collision, the momentum of Q is 0.3 times 2.4 and the momentum of P is 0.2 times 0.4. After the collision, we've got 0.3 Vq plus 0.2 Vp. Simplifying the left hand side gives us 0.8. On the right hand side, we'll keep the 0.3 VQ, but for the VP we'll substitute in 1 plus VQ, so we get 0.2 VQ plus 1. If we now expand the brackets on the right hand side, we're going to get 0.2 plus 0.5 VQ. Subtracting 0.2 from both sides and then multiplying up by 2, we get VQ equals 1.2 meters per second. Since we know that VP is VQ plus 1, that means that VP will be 2.2 meters per second. In part 3, we need to calculate the magnitude of the force exerted on Q by the curved surface of the cylinder after the second impact. Well, as the motion of Q is circular, that means there must be some centripetal force acting towards the centre of the circle. We'll call that force F. And if we resolve towards the centre of the circle, we know that that force must be equal to mv squared over r. The mass is 0.3 multiplied by 1.2 squared, or divided by r, which given in the question is 0.4. And if we put that into our calculator, that gives us 1.08 newtons.